Hi everyone! So in this video we are asked to find the dimensions of a rectangle, right, of the largest area that can be inscribed in a semicircle of radius 3, right. So we are told that the radius of this circle is 3, okay, and very nicely they've put a center for us over there. So from the center to the circumference of this semicircle, we know that the radius is equals to 3 units, right? Now, what do we need to optimize, right? What we need to optimize is the area, okay, of the rectangle, right? So let's put in some variables into our diagram, right? So since we need to optimize the area of this rectangle, which is inscribed, right, we can call, right, this side over here, okay, we can call it the length, L, right, and we can call this side over here, right, we can call this the width, right, and we can show that with the symbol W, right, and we know that the area of this rectangle is simply going to be given by length times width, right, and this is from basic algebra, right. But the problem is with this specific equation at the moment is that it's in terms of two variables, right, and in order for us to carry on with the operations of calculus, right, we need to get this area formula down to one variable, okay, so that we can actually differentiate. Okay, I'm actually going to then simply just call this A for area is equals to length times width. Okay, so now we need to find ourselves another equation, right? So we call this one our optimization equation. So what we need to find now is what is called the constraint equation, right? And the constraint equation is basically the equation that sort of like tells us what we are allowed to work with, okay, what we can work within, right? So for this specific example, right, we need to notice that from the center to anywhere on the circumference of the semicircle, right, we have the radius r, right? So it will be useful to label in a useful radius, right? The one we have right now is not helping us very much, right? But we can see that this radius can rotate along the circumference of the semicircle, right? And a useful radius to label would be one from the center to the corner of this rectangle, right? This is a useful radius to label. Okay, so this is radius r is equals to 3 units, right? Why is this a useful radius to label? Well, because we've been told that what we are working with inside of this semicircle is a rectangle, right? And we know that the interior angles of a rectangle are all 90 degrees, right? Which means that we have now formed a right-angled triangle within our semicircle, right? And then something else that we need to know is that the opposite sides of a rectangle are always equal. So this side is equals to this side, and this side is equals to this side, right? Now knowing that, right, when this rectangle is at its maximum area, right, the center of the semicircle, right, will coincide with the midpoint of this length, right, meaning that we can then have this length, right, from this edge to here to the center of the semicircle as W over 2. Okay, so now we have the length of one of the sides of our triangle, right? We can call this triangle ABC if we wanted to. Okay, where C is the center of our semicircle, right? We could also write this down for the examiner, okay? So we could say construct So it's not necessary to write this down, but if you wanted to, you can. Right. Now, we can actually develop a constraint equation for ourselves. Right. So in triangle ABC, right, you have that L squared plus W over 2 squared, right, must equal to 3 squared, right? And this is the theorem of Pythagoras, right? So applying the theorem of Pythagoras in triangle ABC, we have that the length L plus the length W over 2 squared, right, must give us the radius squared. Okay, so we can solve this equation for W squared, right, as our subject, right? Doing so is going to mean we're going to have W squared over 4, right? Means that over here we're going to have 4 times L squared over 4, right? So then therefore W squared, okay, is going to be equals to 3 squared times 4, right, minus 4 times L squared. Okay. Now, because W and L are both the length, right? So the length and the width of our rectangle, right? We can't have those two values being negative, right? So we are only going to be considering the positive square root of this, right? So then W is just simply equals to only the positive square root of 9 times 4 minus 4L squared, right? Now you can see that we have a common factor of 4, right? And pulling that out, okay, is going to allow us to then take the square root of 4, which is just 2. Okay, so we can rewrite this as 2 square root of 9 minus L squared. Okay. So this is now acting as our constraint equation, right? We can now take this constraint equation, right, and substitute it back into our optimization equation so that we can reduce our optimization equation down to only one variable, okay? Namely, we are now going to have the area, right, of this rectangle as a function of its length, L, right? So A of L, okay, is going to be equals to L times the width, which we now know is 2 times the square root of 9 minus L squared. Okay? And when we think about the domain of this function, right? So the domain of A, right? A, right, is dependent on L, right? So we're going to have L is an element. Okay, we're going to use open brackets because obviously there are values of L that we can't obtain, so that this situation remains true, right? So the first value of L that we can't obtain is a value of 0, obviously. Okay, so the maximum value that L can attain, right, is obviously a value less than 3, okay? Because our semicircle itself, right, has a radius of 3, and L has to be governed, right, by the Pythagoras theorem, right? So L itself, even though substituting L is equals to 3 into the equation, right, still gives us a valid answer. We can't include that value of 3, right, because the radius itself is already 3, okay? So if we have that L is 3, right, then that means that we have no width, right? Because in order for the Pythagoras equation to still hold, if you're saying that L is 3, then you have 3 squared. For the equality to still hold, this must then be 0. Okay, so that means that we are not going to have a width, right? Which means we have no rectangle, right? So the domain of our area function, okay, is going to be L, an element between 0 and 3. Okay, so now we can further simplify this area equation, right? So A of L, and write it as 2L, okay, times the square root of 9 minus L squared. Okay, So now we actually have our optimization equation in terms of one variable, okay, which means that we are ready, okay, to take its derivative, right? Now, in order to take the derivative of this specific area equation, so a prime of L, right, we can note that we have the product of two functions, right, where we can take 2L as our first function, okay, and we can take the square root of 9 minus L squared as our second function, right. Then applying the product rule. So the product rule says that we take f prime, right, which is, we can call f this function in blue, right, so f prime is going to be 2, right, times g, okay, so the second function left alone, so 9 minus L squared, okay, and this is plus g prime, okay, now our g function is the square root of 9 minus L squared, right, when we know that the derivative of a square root function is always 1 over 2 times the square root function, okay, and we just keep whatever is inside, and if whatever is inside is a complex function like what we have, right, we then need to apply the chain rule, right, and take the derivative of the inside function, which in this case is going to be minus 2L, okay, and then we need to multiply this by f, so 2L, so we have a prime of L, okay, is equals to 2 times the square root of 9 minus L squared, right? This negative can multiply this positive, making this a negative, right? One of these 2's, okay, can cancel out. So the 2 here in the denominator can cancel out with one of the 2's over here. Okay, this then means that in our numerator, we've already dealt with this negative. We now have 1 times L times 2L, right, which is going to give us 2L squared, right. This is still divided by the square root of 9 minus L squared. Okay, so now we have, okay, the derivative function, right, of our area formula. Okay, so we are now ready to set this equal to 0. Okay, so we then set a prime of L equal to 0, right? Doing this is then going to help us to find our critical values, right? If you set this equal to 0, you are then going to have the square root, 2 times the square root of 9 minus L squared, simply equal to 2L squared divided by the square root of 9 minus L squared. Okay, then we can multiply both sides of this by the square root of 9 minus L squared. That will leave us with 2 times 9 minus L squared, right? This is equals to 2 times L squared. Okay, dividing both sides by 2, right, we will have 9 minus L squared is equals to L squared. Okay, adding L squared to both sides will then leave us with 9 is equals to 2L squared. Okay, further simplifying, remember L is a length. Okay, so we're only going to consider the positive square root of this, right? So taking the square root of both sides, we're going to have that therefore L, okay, is equals to the square root of 9 over 2, right, which simplifies to 3 over the square root of 2. Okay, so now we have our dimension for the length, right? We can then take this and substitute it back, okay, into our equation for the width of our rectangle, right? This will then give us that W, right, is equals to 2 times the square root, right, of 9 minus L squared, right, And well, I can take the value of L squared from here. It's simply 9 divided by 2. Okay. Then we will have W is equals to 2 times the square root, right, of 18 over 2 minus 9 over 2. Okay. Then we have W is equals to 2 times the square root of 9 over 2, which simplifies to W is equals to 2 times 3 over root 2. Okay, so this is then the dimension for L, and this is the dimension for W, right? It's always good practice, right, just to do a verification check, right, that the value that you obtained from setting your A prime formula equal to 0, in other words, from setting your derivative equal to 0, right, that actually gives you your maximum or your minimum point, depending on what the question was asking you. Our question was asking us to find the largest area. Okay, so we want to verify that L is equals to 3 over square root of 2 is in fact a maximum, right? And we can do this by using the first derivative test. Okay, so into our A prime formula, right, we have this critical point of 3 over root 2. Okay, so when using the first derivative test, right, we need to pick for ourselves test values, right, to plug into our derivative function, right, and the derivative function is then going to tell us, depending on whether we get a positive or a negative result, right, that the original function A, right, which is mapping the area of our inscribed rectangle, it's going to tell us whether that function is increasing or decreasing in the interval. Okay. Now, we also need to remember that these values that we are plugging in are not only just critical values, they are actual values of L, right? And we saw that the domain of L is only between 0 and 3, and it can't equal 0 and it can't equal 3, right? We saw that the value of 3 divided by root 2 is 2.1 something, right? So on the left of this critical point, we can choose a test value of, say, 1.7. And on the right, okay, we can choose a value such as 2.3. Okay. Then we just need to substitute these test values into our A prime formula. Okay, so let's start with 1.7. Okay, we see we get a positive result. Let's then look at what happens at 2.3. Okay, we get a negative result, right? So the gradients, right, of tangent lines on the graph of A in this interval, right, are increasing because we've got a positive over here. So the gradients over here are increasing, right? We know that the gradient at 3 over 2, right, because it's our critical point that gave it, then in this interval we got a negative result, which means that the gradient of tangent lines in this section are decreasing. So our original function A is increasing to the left of 3 divided by root 2, right, and decreasing to the right of 3 divided by root 2, right, which means that 3 over root 2 actually is a local maximum. Okay. You could have also used the second derivative test to confirm this, but you can see that that will require you to find a double prime, which is going to be a process, right? So for this case, using the first derivative test is much easier, right? So you've confirmed that the dimensions are L is equals to 3 over root 2, and W, the width, okay, must be equals to 2 times L, right, which is equals to 2 times 3 over the root of 2.